Greetings everybody, welcome to the latest edition of the Physics Corner with Dr. Christopher Sorolla. Today we're talking about electric generators. So in a different video, we discussed electric motors. And what's the difference? They sound like they kind of do the same thing. They sort of do opposite things. An electric motor uses electricity to make things move, or motor if you will. An electric generator generates electricity. It uses motion to make electricity, so they do the opposite. So we're talking about the generator in this particular episode. There's a separate video that talks about an example of electric motors. So let's imagine we have the following. This electric generator is spinning with a frequency of 50 hertz. To remind everybody, hertz is cycles per second, so it'll make complete loops, if you will, 60 times per second. It has 500 turns or coils of wire in this. The coils of wire are immersed in a strong magnetic field of 4 Teslas. And the size, or the radius of the coil, is 5 centimeters. Now, we're assuming for our purposes that the coils will be round or circular in shape. That is not necessarily how you have to do it. You can have other shapes of coils, but that's very common. It's the simplest kind of shape to make, and so on and so forth. So we'll do that here. Okay. So how much EMF is generated by this generator, or how much voltage is generated? So the formula for EMF, or this kind of voltage generated by an electric generator, looks like this. So this is the EMF. This is angular frequency, number of turns, magnetic field, and a capital A is cross-sectional area. Now you notice a couple things. From what we're given, we are given the number of turns and the strength of the magnetic field straight up. So we have those directly. But we don't have omega. You don't have capital A. So this is very common, by the way, in these kinds of problems to make you go through these extra steps. So let's do those together. So angular frequency and quote-unquote regular frequency are related together by this particular formula, right? The 2 pi tells you that we're going to transition from just a regular frequency to radians per second. So instead of cycles per second, we get that. So we have 2 pi. The frequency was 60 hertz, like that. And when we calculate that, I'm going to round off to the nearest third digit, we get 377 radians per second. So notice also, like I said before, we not only change the number, we're also changing the unit somewhat. This reflects, again, the idea that this is a rotational idea, ultimately at its core. All right, what about area? Area of a circle is pi r squared, pi radius squared, right? You might remember that. So pi, now the radius is 5 centimeters, or let's put this in terms of meters, so we have our standard units, 0.05 meters. I have to take that whole thing and square it, and when I do, I get this as my answer. Okay, it looks kind of small, but remember this is units of meters squared, and meters squared is pretty big if you think about it. So all right, so we've got our coil of wire rotating at this rate around our magnetic field, and that number of turns of wire. Now it's just basically a plug-in chug sort of idea. So omega NBA, like this. So 377 radians per second for omega, 500 for the number of turns. Notice there's no units, it's just a number. Magnetic field was given to us as 4 Teslas, and the cross-sectional area, and that's what it is, by the way, a cross-sectional area. It's not the area of, say, the cylindrical shape of the coil. It's the cross-sectional or circular area of the coil, like that. And in this particular case, we end up with this number of volts. So calculation-wise, it's not too difficult a problem. It's actually kind of straightforward, I think. You do have to recognize that you're taking some extra steps sometimes to get, say, omega and A like that. Something else to mention, these numbers are more or less artificial, but this isn't this voltage that you would encounter in everyday life, right? So for example, the voltage that comes out of a wall socket at your house is almost always 120 volts. In some specific cases, like say, for example, if you've got an electric dryer hooked up in your home, that might be a 220 volt line, which are both much, much less than this. How do we get from, say, a number like this to numbers that you actually use in a home? That's a separate video to make. I'll simply say that, yes, there are objects or devices called transformers, which will do that trick. But that's a separate discussion and a separate video. So today, very, very short, and I hope you don't mind. Technical support staff is Sydney Galtra and Sophia Turner. These videos are funded by the University of Mississippi and University of Southern Mississippi. I'm your host, as always, Dr. Christopher Sorolla, saying goodbye from Hattiesburg, Mississippi, and clear skies.